Okay, we'll be looking at some questions on things like the chi-squared test, correlation coefficient, line of best fit, and compound interest, currency conversion, depreciation, commission, as we prepare for this test on two-variable statistics and financial mathematics. Well, starting with number 1, where we've been given a table of observed results. It looks like it's going to be a chi-squared test. And I notice that the totals have already been given. So these totals are not part of the actual information. The matrix that I'm going to end up putting it into the calculator just is these 6 numbers right there. Everything below them are sums, and everything to the right are sums. And the stuff on the top and on the left are, of course, the titles. So the question posed is whether they are independent. So part A, we need to show clearly that the expected number of males. So you remember when we see show, that you can't just use the calculator. You're not allowed to use a simple technology method. We actually have to demonstrate a calculation by substituting into a formula. And we know that expected number can be found by taking the sum of the row times the sum of the column divided by what I call the supersum. You'll notice, by the way, I've noticed a couple of you have made this mistake. So the supersum is just the sum of these, or the sum of these. They're both going to give you the same thing. But it's not both. You don't add these and these together. You only add one set of them, and you'll end up getting the same. That's the total number of people in the survey. Right, so the expected number of males, that's right here, achieving a grade of 5, 6, or 7, that's right here. So we're talking about the one that's going to go in that particular cell. So in order to get this one, we have to take the sum of this cell's row, which is 9,000, times the sum of its column, which is 11,000, and we'll divide by the supersum, 20,000. So let's do this. Now with a show that question, it doesn't hurt to be a little bit more explicit than usual, to make sure that we do get both marks. I imagine that right there is probably both marks already, but nevertheless, if it comes out to an unrounded, oh there we go, it comes out really nicely. So as long as I do write down an unrounded answer where necessary, here it's not, and I write down the answer itself. Part B, a chi-squared test is set up. State the null hypothesis. The null hypothesis is the one that says that they are independent, and here we're dealing with gender and grade. So the null hypothesis is that grade and gender are independent classifications, or if you prefer, independent variables. But I think the best word here is maybe factors. Not sure. State the number, oh, and by the way, I'm just going to say that's the null hypothesis. There we go. State the number of degrees of freedom. So this is where you have to be careful that we do not include the sums or totals row and column. So we've got 2 rows. So the degree of freedom, we've got 2 rows minus 1. And we've got 3 columns of data, 3 minus 1. And that gives me 1 times 2. And my degrees of freedom is 2. Calculate the value of chi-squared. This is where I'm going to have to put it into the matrix. So I'll say second matrix. I'm going to edit matrix A. Because it's 2 rows by 3 columns, so you always go rows by columns so that the matrix looks correct. And let's enter the values. So these are the observed values. 5,000, 3,400, oops, 600, 6,000, 4,000, 1,000. Oops. And once we've got it in and double checked it, let's exit. And now we'll go to vars. Shoot, that's not right. Let's try second vars. Oh darn, I'm lost. How about stat? Oh, there it is, stat. Tests. And let's go to the chi-squared test, option C. And we're going to do a chi-squared test where our observed matrix is indeed the one we entered as matrix A. The expected will be output into matrix B. I could look at it if I wanted to. Let's calculate it. And we discover that the value of chi-squared is 39.957. And I could round to 3 significant figures, but why bother? And it says that the critical value of chi-squared at the 5% significance level is 5.991. What can we say about gender and grade obtained? Well, because chi-squared is greater than the critical value of 5.991, that must mean that the variables are dependent upon one another. So we are going to reject the null hypothesis. And we can state then that gender and grade are not independent. Or you could say that they are dependent. Are not independent factors. And this is kind of a little bit unusual for a chi-squared to get actually dependent. So let's just have a quick look and see whether that makes sense. This to me is a little bit of a surprise, because I can see that we've got similar ratios between males and females in each of the... Oh, I see. That's actually quite a marked difference, isn't it? You wouldn't have expected such a huge difference, almost double the females when these ones were so close. So perhaps it's not a surprise after all about having some dependency. All right, let's move on to number 2. 10 students were given 2 tests, one on math, one on English. And there we can see the results. You'll notice that mathematics is the X and English is the Y. So if you're going to graph this on a scatter plot, please make sure that you've got the axes in the right order. So mathematics, the first variable they give you is always the horizontal one. And then the English is going to be the vertical one. So English, math. Calculate the correlation coefficient. Some of you were asking as you were working on these review questions, why is this worth 6 marks? And I think that it's because it's an old question where they used to expect you to sort of write the list of the x and then the list of the y's. And you remember that we did this with the spreadsheets, the x squared, the y squared, the xy. And then we take the sums at the bottom and then we fill them into that massive formula with all the square roots on the bottom. And I don't know if you remember all that stuff, but anyway, if you did all of that work, of course it would be worth 6 marks. Nowadays, this question is only going to be worth probably 2 marks. And so let's calculate that correlation coefficient. In order to do this, I'm first going to have to turn on my diagnostic so that when I do a linreg on my x data and y data, the r value does appear. So I'm going to say mode, and I'm going to press up in order to find the place where stat diagnostics can be turned on. There we go. Now my diagnostic is on. Let's put in the data. So stat, I'm going to edit some lists. In list 1, here's the tedious part. Fast forward if you must. My y values. there we go. So now I should be able to exit, and I'll press Stat, Calc, linreg, and if I don't put in the lists, the calculator will assume that my L1 is my x values and my L2 is my y values, and I think that you should always make sure your x values are in your L1 and your y values in your L2, so that we can simply do linreg and say enter straight away. Not only can we see the values of the slope and the y-intercept in our line of best fit, but we can now see the r value is 0.711. Now, this is not actually a particularly strong correlation. I don't have it handy to be able to pull up now. Maybe you can find it in your notes, but you tend to need a much larger r value than this in order to have strong correlation. And it's only if you have strong correlation can we actually make predictions for the future. So, and maybe it's worth reminding you about extrapolation as well. That there are two times at which you cannot make a reliable prediction. One way is the situation here where we don't have a sufficiently strong correlation. So I could say, for example, in this case, we don't have a sufficiently strong correlation. I mean, you want your r value to be at least 0.9 or 0.95, like 90-95% in order to have a strong enough correlation to bother making predictions. So we don't have a sufficiently strong correlation since r is not very close to 1. And thus cannot reliably make such a statement. As someone who does well in math will also do well in English. There's not enough evidence to be certain. Only 71% certain? That's not really very useful. So yeah, let's look for an r value of at least 90-95% or so in order to be able to say that there's correlation. And the other time you have an unreliable correlation is when you're dealing with extrapolation, where let's suppose I needed to find the English grade when the math grade was, say, 20. And that's so far well outside the set of data, and that would be extrapolating, and we can't assume that the relationship between the x's and y's, which is of course a very weak relationship, is going to extend beyond this particular range of mathematics scores. Alright, number 3. Sven is traveling to Europe, withdraws $800, converts it to euros. I like currency exchange problems, and I think I'm just going to set up ratios every time. And so we've got $800, which we're going to be converting to euros. I don't know how many yet. The local bank is buying euros. Well, that's not what's happening, is it? The bank is selling me euros. So I'm going to be taking the sell rate, because the bank's selling me the euros. And there I've got $1. You notice the dollars are on the top, and this is 0.766 euros. And so to cross multiply, x times 1 is x, and 800 times 0.766. And there's some of you that might have realized straight away that we simply want to multiply $800 by 0.766 because we're expecting to get a smaller number than what we currently have, because the value of a euro is greater. I'll show you what I mean in a minute. So 612.80 euros. And so yeah, what I'm showing you is that you'll notice that $1 gives you less euros. And so we're expecting a smaller number of euros compared to the original $800. Alright, Part B. Suppose the trip is cancelled. How much will he receive if the euros in Part A are changed back to dollars? Alright, so 612.80 is his euros. We're converting that back to dollars, and this time he's going to be, this time the bank is going to be buying his euros back. And so we're going to be using the buy rate of 0.785 euros over $1. You could have both of these fractions upside down if you want. Let's cross multiply then. We've got x times 0.785, that's 0.785x. And we've got 1 times 612.80. And that means that our x is equal to 612.80 divided by 0.785. And of course, again, some of you might have been able to move straight to that step, realizing that we need to divide by a fraction, because when you divide by a fraction, you end up getting a larger number, and we want to end up with a larger number because we're converting back to dollars, and dollars, of course, you get more dollars for the number of euros, as we can see from these exchange rates. And we got to use this exchange rate because the bank is now buying your euros. So let's do the calculation. 612.80. And by the way, you'll notice back here that I had to add an additional 0 compared to what my calculator said, because currency should always be expressed with 2 decimal places. Very important. Alright, so now I'm taking 612.8 or 80. They're the same number, aren't they? But I just need to express it as 80 when I write it on paper. Divided by 0.785. And that puts me back up to $780.64. $780.64. Okay. And then Part C. How much has Sven lost after the 2 transactions? Well, we're going to take our original $800, and then he ended up with $780.64. So let's see what the difference is, and that will be the amount that he lost during the 2 transactions. 1936. And that's dollars, isn't it? Because both of these currencies are dollars. And now we need to express our answer as a percentage of Sven's original $800. So this 1936 that was lost, what percent of his original 800 is that? So we'll say 19.36 divided by 800. So we'll find out what proportion, and it was 0.0242, and we can move the decimal place over twice in order to get 2.42% is the amount of commission, I suppose, that the bank has made through this double transaction. They took 2.42% of his money.